Hello, everyone. My name is Jiang Wang, currently a postdoctor at Institute of Theoretical Physics of Chinese Academy of Science. It's a great pleasure to have an opportunity to present my recent works of chameleon dark energy as a possible solution to the Hubble tension. This talk is prepared for the workshops on the Hubble tensions at University of Southampton. Um, as we know that the Hubble tension is a long-standing inconsistency with the persistent significance between various independent local direct measurement on Hubble constants and the CMB global constraints fitted by the lambda CDM model. So at the left-hand side, I have collected as many measurements of Hubble constants as I can find in the literature that could be fitted into a single figure. The dashed line here presents the supernova measurements calibrated by different distance ladders, such as Zephyr, TRGB, and Maris. The solid line here presents the other direct measurement independent of a distance ladder, such as the surface brightness fluctuation measures, Tulin-Fincher relation, strong length intent delay, and the gravitational wave standard sirens. The red strip line here presents the sample constraints from the Planck 2018 data. I also present the other early measurements with the red rectangular regions. The first three red regions represent the low L, the full L, and the high L data from the SPT polarization. The next four red regions present the EE spectrons data from the Planck on ACT polarization, SPT polarization, and SPT third generations. Both of these red regions show us some suspicious strips with respect to the full CMB data. The last three red regions present the CMB independent constraints from the BAO plus BBN constraints, the extragalactic gamma ray backgrounds, and inverse distance ladder measurements from the dark energy serving constraint on the BAO calibrated by the supernova data with the same B prior on the sound horizon. What we can learn from the current constraints so far, I summarize the 5 points here. The first point is that there seems no single systematics to all the local direct measurements with or without distance ladders, as they are largely independent. And second, there are disagreements with the supernova data calibrated by TRGB from the Rees and the Friedman group, and also in the strong length intern delay measurements from the TD Cosmore and the Holico group. And third, the gravitational wave standard siren measurement is consistent with most of the global indirect measurements, although we have large uncertainties in the localization of specific gravitational wave standard siren events. And fourth, there are some suspicious shifts from using either the high L data or the EE spectrum data only with respect to the full CMB data. And we don't know the cause of these shifts. And the last point is that the CMB independent constraints from either the BAO plus BBN constraints or the inverse distance ladder measurements seems to hint at some new physics in the early universe if you think the late-time universe should be homogeneous at a large scale. But there's some caveats in here, as we'll see later. The current proposed solutions are usually classified into the early time solution and late time solution. The early time solutions change either the expansion history or the recombination history. And the late time solution could be either homogeneous or inhomogeneous. The early time solutions could change the expansion histories by either adding some early dark energy or dark radiations, which could be either free streaming or non-free streaming. The free streaming dark radiation seems to be not favorable because it could also change the damping tail of the CMB power spectrum, even if it could preserve the first acoustic peak. So therefore, a non-free streaming dark radiation might be favorable. For example, for this strongly interacting neutrino model. The early times solution could also change the recombination histories by primordial magnetic fields, the non-standard recommendations, and very fundamental constants, to name just a few. The late times homogeneous solutions really refer to some late time dark energy with phantom-like transition and low redshift, or the interacting dark energy. For example, some decaying dark matter model into dark energy. The late time inhomogeneous solutions really refer to the underdensity, either caused by the cosmic voids or the modified gravity. Here today, I want to present the first late time inhomogeneous solutions using the overdensity, and we call it the chameleon dark energy. It is also worth noting that there are many models on the market which might seem to be illusionary due to some enlarged uncertainty of the extended parameter space or the blind data combination with the local Hubble constant measurement. So some models achieve to solve the Hubble tensions simply because they have a larger parameter space with a larger uncertainty, but the central value does not change. This kind of solution should not be, this kind of solution is not so feasible. Yeah. The second kind that some models claim to solve the Hubble tensions only in the case when they blind combined the early constraint with the local Hubble constant measurements. If they remove the local Hubble constant measurements, the model seems just like the lambda CDM model. And this kind of model is also not feasible. Recently, there are much debates over the early time solutions. For example, in this paper, they also give a very general argument. To put it in a simple way, there's like the first picture here. To have a full consistency of the CMB peak with the BO band and the Schultz measurements of Hubble constants can only be achieved at the price of a higher value of omega mh square. However, with such a higher value of omega mh square, we are in tension with the galaxy lengthening data, for example, from the dark energy surveys or the kilodegree surveys. So in a figure on the right-hand side, with the exceptions of the strongly interacting neutrino models, there is consistencies in the rest of the models. If you look at the tendency, the model with a low omega mh square either fail to achieve a sufficiently high value of Hubble constants or are in tension with the galaxy clustering data of the BLO. The model with higher value of omega mh square will in tension with the galaxy lengthening data from for example, the dark energy survey or the kilodegree survey. So these general arguments on the early time solutions also agree with some earlier study on the dark energy model, for example, the 43 paper. But there are some other evidence against the early time solutions. For example, the consistency test of the sound horizon between the matter radiation equality and the recombination of this paper. There's another consistent test of the sound horizon between the recombination and end of the drag epoch of this paper. Therefore, there is a very little room for us to modify the early time universe. So let's look at the late time solutions. The late time homogeneous solutions are usually strongly constrained by the inverse distance ladder measurements. The inverse distance ladder constraint is independent of the late time homogeneous dark energy, yet it is still consistent with the early time global fitting result. This is the usual argument that the possible modification should come from the early time universe. The second argument for the late time homogeneous dark energy solution is that the Hubble flows constraints. In the following two papers, the late time dark energy with the phantom transition has been strongly constrained. So in the first plot, by placing transitions at a very low redshift, for example, d much smaller than 0.1, such a model can raise the local expansion rate to the 74 or even beyond without significantly changing any cosmological observers at redshift larger than 0.1. However, the problem with such a solution is that if the transition occurs at redshifts smaller than 0.01, raising the Hubble constants does not actually resolve the origin of the Hubble tensions, which resides in the Schurz calibrate supernova in the Hubble flow here. Whereas if it occurs at a higher redshift, for example, in this yellow line here, then it is strongly constrained to be much smaller than the required magnitude to fully resolve the Hubble tension. So therefore, in the second plot, the late time dark energy models constrained by the Planck plus VLO data does not significantly improve the Hubble constant value, as shown in this yellow line here. In the third plot, the author fits several physically motivated dark energy model and derive the combined constraints from the calibrator and the present supernova data, and simultaneously inferred Hubble constant and dark energy properties. They find that the assumption on the dark energy model does not significantly change the local distance ladder value of the Hubble constants. So nevertheless, there are some exceptions of the interacting dark energy model. In this case, the decaying dark matter into dark energy, where it still requires further investigations that how such a model could extract the above arguments on the late time solutions. Now let's look at the late time inhomogeneous solutions. The inverse distance ladder argument for the late time solutions is could actually be avoided if we allowed for late time inhomogeneous solutions. The most popular late time inhomogeneous solutions refer to the underdensity from a large local void. There are many studies on the existence of such large local voids from two different data analyses: the luminosity distance data from the Galaxy survey and the supernova data from the Hubble flow. The difference is mostly announced that in this paper, where the large local void is clearly visible by eye from the luminosity data, but it is not favorable using only the Hubble flow supernova data, as shown in this green region. So therefore, it is worth noting that the treatment of this paper is quite general without specific approximations when fitting the luminosity distance. So therefore, it's unclear that such disagreements is caused by the different Hubble constant profile at the local positions or some systematics in both measurements. So today I want to show you the other possibility using the overdensity in the model of chameleon dark energy. The idea is very simple and easy to see. How does it work for the Hubble tension? If the chameleon fields coupled to an overdensity region, it could be trapped at a higher potential energy density, playing the role of effective cosmological constants, therefore driving the Hubble expansion rate locally higher in that region than that of the background region with lower matter density. For our toy model, we have a three parameter, the alpha, lambda, and n. The lambda could be chosen freely since it could be compensated by a redefinition of alpha. And alpha could be fixed by the boundary conditions that should be matched the CMB results outside the overdensity region. Uh, then to reproduce the Schur's measurement of the Hubble constants inside overdensity regions, the required matter density and its corresponding matter density contracts can be easily solved to be around 20%, irrespective of any choice of n. Therefore, the toy model for the overdensity region with a top hat shape, there's effectively no free parameter that I can adjust with except n, which itself is highly insensitive. For more realistic case of our local universe, as we will see later, the only input is the local matter density fraction profile, omega m r. Since dark matter cannot be directly observed on lasers, we therefore use the galaxy tracer for the total matter distribution with input of the galaxy bias parameter B and the two-point creation functions of the matter clustering. The two-point creation functions could be given globally by a simple approximation or from the real data of the BOSS data release 12, CMAS, and the low Z sample. And this will gives you the average local matter density profile over every point in the survey regions. The galaxy bias in this case is really taken between 1 and 2, as they did in the BOSS team. We can also define a local two-point creation function because we are in a very spatial positions in the local universe. Therefore, the average, the matter density profile cannot describe our M-based matter density profile. Therefore, we can define a local two-point creation function simply by counting the number of galaxies around us with respect to a random sample also provided by the BOSS team. This will reproduce the well-known structures of local voids, local supervoids, CFA2 great bore, Sloan great bore, and BOSS great bore, as you can see here. This is the Sloan great bore, where you cannot see the BOSS great bore here, but this is the CFA2 great bore. Finally, with the input of the local matter density profile from the real data, we can solve the Hubble constant profile from the LTB version of the Friedman equation. As you can see that our results could be simultaneously incorporate most of the local measurements. The very low distance part cannot be traced simply because the breakdown of the LTB isotropy in the very local region. So this is where our model will fail. At very large distance, the galaxy surface cannot be traced because some limitation on the observation time and sensitivity. So at very large distance, we should trust the results from the global two-point creation function, which will reproduce the CMB constraints on the Hubble constant. Now let's focus on the intermediate regions. Since there is a large overlap between the BOSS data release 12 and the supernova data, as you can see here in this region with the black triangle. Therefore, the local two-point creation functions could faithfully reflect our local matter density profile. Therefore, the supernova data calibrated by the Sophia measures, TRGB, or even the Holocron measurements could be explained by our Hubble constant profile from the local two-point correlation function with the input of the real data of a galaxy survey. And we know that in the real data galaxy survey, we have some great word structure. So basically, we find a close correlation between the Hubble constant, the local Hubble constant measurement, and the local large-scale structure. And the local two-point correlation functions is not feasible at the large distance, as we have discussed, due to the limited sensitivity and observation time, so that the CMB constraint should be recovered by the global two-point correlation functions simply because the emergence of the cosmic homogeneity. And there are some other measurements, for example, the gravitational waves, events, the surface brightness variation, and lasers. They actually lie partially outside the survey region of the far spectrum 12. Therefore, the local two-point correlation functions from the Boss two-point correlation function cannot faithfully reflect their M-based matter density profile. Therefore, we might need some other complementary survey, such as this 2M at the cross and low Z, and dark energy survey at a high Z. So in fact, there are actually some hints for the suspicious trends of the Hubble constants constrained by the data of different redshift beams. It seems that the higher redshift beams of the data might constrain a lower value of the Hubble constants. So this is consistent with our dark energy model, with our Chameleon dark energy model, that higher redshift beams of the data live in a more homogeneous shell around us. Perhaps a very quick check would be that to look at the TRGB paper, we can find the redshift distribution of the best fit value of the Hubble constants constrained by each individual supernova data calibrated by the TRGB in the Friedman paper. If we can find such trainings, then we have some supporting for our model. Now let's come to our conclusions. So our Chameleon dark energy is the first model of the late time inhomogeneous solutions, utilizing the cosmic over density to the Hubble tensions by the lifted potential energy density from Chameleon coupling to the great wall over density in the current galaxy survey. Here is some discussions. First, our Chameleon dark energy has effectively zero parameter, since N is insensitive to parameters, and alpha can be fixed by reproducing the CMB at the cosmic scale. And the galaxy bias could be either choose between 1 and 2, just like the Boston did, or they can be removed from the model if our local matter density profile could be measured directly by some other observational methods. And second, our Chameleon dark energy model drives the late time accelerations by the quintessential effects from the trapped effective cosmological constants instead of the self-accelerations ruled out by the Langdon theorem, as you can check in the paper. And the fixed force introduced by the Chameleon fields is actually 0.01 millimeter, as you can check in the paper, which is actually within the allowed constraints of the modified gravity theorems. And last, our Chameleon dark energy model could also potentially solve the sigma A tensions, since an overdensity with additional negative pressures introduced by the Chameleon dark energy tend to smear at a larger scale until reaching a new viral equivalence due to a decrease in pressure with decreasing matter density. And thank you, that's all. And any question will be welcome.